Okay, so sorry for this being a seminar, but not a colloquium. Anyways, it's a pleasure to invite Gourab Ray from University of Victoria, who will be telling us about graphical expansions of Ising as factors of IID. Please go ahead.
Okay, thank you. Thanks, Nishant. Thanks for having me give a talk here. So I'm going to report on a recent work with Omar Angel and Inon Spinka. By the way, can you hear me okay, everyone?
Perfect.
Yes. Okay, very good. So this project came out of a question posed by Tom Hutchcroft in his paper called Continuity of Ising Model, especially on non-amenable graphs. And so this question sort of was similar to my interest at this point. So it's kind of an obsession of mine recently, which is to prove various statistical physics models and understand whether they're factors of IID or not. Okay, so this talk is about something called a factor of IID. So let me start by defining what that is. So I'm going to start with an infinite vertex transitive graph. So for so if you want a concrete example, think of two examples. One is ZD and one is the deregular tree. So suppose you have some automorphism invariant stochastic process. So just you have some stochastic process which whose distribution is invariant to changing the root. So in ZD, you can think of the space of automorphisms is translations, reflections, etc. But sometimes in ZD, people just take translations to be the set of automorphisms that they care about. So suppose you have a stochastic process like this, and you are asked, and the question is how different it is from an IID process. Okay, so suppose so the definition of factor of IID is that X is a factor of IID if there is some IID process. So you're free to choose your IID process. Usually just taking IID uniform 0, 1 is more than enough. And the question is, can you write X as a function of this IID process? And this function has to satisfy two properties. Okay, so first of all, it has to be measurable. And secondly, it has to be automorphism equivariant, meaning that this function essentially should not depend on the location of the root. Okay, so there's a question in the chat.
So Shikhar, you can unmute yourself if you want. I think he does not want to unmute.
Okay, he just said it is.
I didn't ask any question.
Okay. Okay.
Kaushik wrote that he cannot see the screen, to which I wrote it is.
Okay, okay, very good. Okay, so
you can't see the screen?
Yeah, I can't see, but I'll join from my iPad and just check. Maybe it's a problem with my laptop. Just give me a second. Yeah. No, you carry on. I'm on both. Yeah.
Okay, so I mean the audience is small enough, so maybe we can wait 1 minute.
In the meantime, I had a question.
Yeah, please go ahead.
Your process is both on vertices and on edges, right? So there's both site and vertex, and here what you're describing below is just on sites, right? Not that it makes a huge difference, but
yeah. So I mean, so in the definition, I took the IID process on vertices, but yeah, essentially it's not that big a deal. You can also talk about
finite degree, then it doesn't matter, I guess.
No, yeah, of course. If it's if it's vertex transitive and bounded degree, it's not such a big deal. But this is the definition I'm going to work with throughout the talk. Okay, so I mean, this IID process will be something attached on the vertices, and I really need this process X to be on vertex and edges both.
I see. So Kaushik, can you see the screen now?
Yes, I can. Yeah, thanks.
Okay, very good. All right, so let's just to get an idea of what this is for those who are not familiar with this concept, let's start with a simple example. So here is a stochastic process for you. So take a IID bond percolation on your graph. Okay, start with this, and then for each connected component, color all the vertices either plus or minus with probability half. Okay, so here is a small picture which I tried to draw, and the question is this a factor of IID? By this I mean X. Okay, so if you have a finite, so there are three cases essentially. So if omega, so this IID bond percolation process, I hope everyone's familiar with that, is definitely a factor of IID because it's just IID. So you can think of constructing S as a composition of the first IID process, which is the Bernoulli, which is the IID bond percolation, and then on it you want to introduce another function which will give you your X, right? So so here is the question maybe for the audience, and the audience is small enough that maybe I can just.
I'm actually very confused here. So what is my stationary process here? Is it just
the signs? So just the signs on the vertices. So it's on the each vertex is either plus or minus, and so you look at every connected component of omega and color it plus or minus with probability half independently. Okay, I should have added independently here.
I see. So you first take the usual bond percolation, then you take all the components, and then you independently color them plus or minus.
Yeah, exactly. Okay. So if omega has finite clusters, maybe let me ask the audience if they have a guess whether this is a factor or not.
I would think that it must be. You're just choosing. It's just an IID on top of another IID, right? So you just take a product and then have some leftmost corner sign that you take.
Exactly. So you have the right intuition. So that's definitely correct. So let me just write it yes, but you have to be a little bit careful. So one way to construct this. So let me give maybe a full proof. Is to first look at omega. So omega has been already constructed. It's an IID process. And then for every vertex, I have to give an automorphism equivariant way of assigning plus or minus to that vertex, right? So I look at the connected component of omega containing that vertex. And now it's finite. So I will stop eventually at some point. And then I have to assign a sign to it, to the whole cluster, and I have to.
Is your set of automorphism just the translations, or you'd want to take reflections and rotations?
So in this case, it's everything. But let's just take translation just to keep things simple. In this example, okay. So now I have to pick. I have to describe how I pick the sign. So here's one way to do it. Just assign uniform IID, uniform 0, 1 random variable on the vertices, and on your finite cluster, pick the one which is, let's say, the highest value, and also assign IID plus and minus on every vertex, and give the cluster the sign which is associated with that uniform 0, 1 random variable with the highest value. Okay, or in other words, you are uniformly picking one vertex from your finite cluster and just assigning the cluster the sign of the uniform vertex. And I just described to you how to select the uniform vertex on a finite cluster by as a factor by assigning, let's say, uniform 0, 1 on each vertex and looking at the highest value. So that's one way to select a uniform point from a finite cluster. Okay, so it seems
sorry, Gaurav. So the question of having the factorization, this is not dependent upon the parameter half, right?
No, yeah. So here the half is just arbitrary for the example. If indeed, if it was any p, the same thing would work exactly. Okay, but this particular construction which I just mentioned is not going to work once omega has an infinite cluster. Okay, so I said pick a uniform vertex from your omega, from the cluster of omega, but that doesn't make sense if there is an infinite cluster. And actually, we'll see later that if some process is a factor of IID, it has to be ergodic. And once you have a unique infinite cluster, then it's kind of clear that the process X, which I described, is not ergodic, because there is a probability half of the probability that there is an infinite cluster of plus is half. Okay, so that's a translation invariant event that doesn't have probability 0 or 1. Okay, so this is a no. So there is no, this is not a factor of IID. Okay, and this is not a factor of IID so in this, if P is anywhere between 0 and 1 without including 0 or 1. Okay. Okay, so then you can ask, well, what if omega is infinitely many infinite clusters? And these are, and these examples are not very exotic. Yeah, please go ahead.
Is it okay if we keep interrupting you, or
no? Yeah, please go ahead.
Yeah. So I actually didn't follow this ergodicity argument so well. Can you just repeat once more? I know that you will get to it later as well, but maybe just so you have a 0-1.
Yeah. So we want to.
Yeah.
We want to use the fact that if something is a factor of IID, it's ergodic.
Okay. So
and if you have a unique infinite cluster, then there is an event which you can. So in this process X, if you look at the event that there exists an infinite cluster of plus, that event has probability half.
Why will it have probability half? It can have probability 1, right? Because my event that it has an infinite cluster, it will have probability 1, right? Especially for example,
infinite cluster of plus. That's what I mean.
Because you can switch between the two. I see. Right.
Yeah.
Okay.
Yeah. Exactly.
Thanks.
Yeah. Okay. So I guess the more interesting case, which is relevant to this talk, is if it has infinitely many infinite clusters. This is not a very exotic example. If you just take Bernoulli, if you just take bond percolation on a regular tree, you will have infinitely many infinite clusters. And there, it's this ergodicity argument is also not clear, because now you have infinitely many infinite clusters, so you can't really find an ergodic event with probability between 0 and 1 so easily. And in fact, we'll see later that sometimes it is a finite, sometimes it is a factor of IID and sometimes not. Okay, so here actually the question is more nuanced, so it's a maybe. Okay, so just to give you a bit more perspective, let's take this example a bit further. And I say that every infinite, so it's the same example as before, except for every infinite cluster, let's say I put always a plus sign. Okay, now this is, let's say, my new process. Now, is this a factor of IID? Now, if there is a unique infinite cluster, how to construct this factor process? Well, you can look at this omega, and since if you go and explore a big ball around a vertex, then with very high probability, you will know whether you're in the infinite cluster or not. So this will give you a measurable function, which will tell you whether the vertex is an infinite cluster or not. And when it's in an infinite cluster, it's a deterministic function. It's always a plus. So from here, it's not very hard to argue that this process is in fact a factor of IID in this case. So and actually the same argument works even if there is infinitely many infinite clusters. So in this case also it's a factor of IID. Okay, so I hope there's some intuition behind what this process, what a factor of IID is, and how one might go ahead and construct such process. So let me also mention in passing, there's another notion of finitary factor, which is not going to be very relevant for this talk. But let me still mention, because I want to mention a few other results. When you have this factor function phi, and if it only depends on a finite but random ball around the vertex, then we say that that process is a finitary factor. So it gives you an even better algorithm to construct your process. Okay. Okay. So what is this? So why do we care about this factor of IID? Yeah.
So is the above process a finitary factor? Your above process is a finitary factor, right?
If there is a finite, if there is a finite cluster, then it is. If all the clusters are finite, then it is. If there is an infinite cluster, then actually no. So
if there's an infinite cluster, right? Because I've explored till a certain time and I still don't know the value. I guess
it's not such a. I mean, that's the intuition, but it's not such a naive argument. You need to. It's a. Yeah. Okay. So let me give you one example. So on a tree, if you take the Ising model with very low temperature, in that case, you also have a unique cluster of an Ising model with plus boundary condition with very low temperature. In that case, you also have a unique infinite cluster of, well, you have an infinite cluster of pluses. In that case, it is actually a finitary factor of IID, even if you have a infinite cluster. So it's not such a naive thing. There's something going on here with this thing, and the geometry of the graph. Okay, so we'll get to that in a bit. Okay, so factor of IID actually came, as far as I know, from ergodic theory mostly. So it basically started from the work of Ornstein, as far as I understand, and it's really a strong form of mixing property. So so sometimes people in ergodic theory talk about Bernoulli processes, and it's really a factor of IID process, but this function phi is invertible. Okay, and in fact, it's not much different from a factor of IID process, because we have a choice of this IID process that we can take. So in fact, if something is a factor of IID, then you can also show that it's Bernoulli. So that's a result of Ornstein. And if a process is Bernoulli or factor of IID, it's actually ergodic, and various forms of mixing conditions are also satisfied. Okay, so it's stronger than all these notions of mixing, which I'm not going to get into, but also it's weaker than certain things. So it's somewhere so if a process is Bernoulli, that's something nice to have. Okay, and it's kind of a recent obsession of mine is to just take a statistical physics model and ask whether it's a factor of IID or not. And as far as I understand, one of the models which have been studied before, and this question has been asked before, is about the Ising model. Okay, so I'm going to define the Ising model later, but whatever I'm going to talk about today is going to be related to these four statistical physics model, and mainly this last one, and that's what this talk is about. Okay, so let me go ahead and define the model, which is of interest today. So this is called the Lupo-1 model. It's going to be related to the Ising model, if you, which I'm going to talk about later. So let's define it on a finite graph. Okay, so you have a finite graph, and the model is defined as follows. So here is the probability measure. So there's some weight for, so it's a percolation model. It's a percolation model on vertices and edges. So every vertex is either open or closed. Every edge is either open or closed. Okay, and the probability measure is simply has weight x for every open edge and y for every open vertex. Okay, so if you are familiar with Ising, this x is related to the temperature of the Ising, or will be related to the temperature of the Ising once I talk about it, and y is related to something called the external magnetic field of the Ising. Okay, so if the probability measure was just this, is proportional to just this, then it's just an IID process, so nothing interesting. But there is an indicator function here. So what is this indicator? It tells you that this whole percolation process is even. Meaning what? Meaning that if you look at the degree of a vertex, plus 1 or 0, depending on whether the vertex is open or not, and if this whole sum is even, then we say that so okay, so if okay, so there is some issue with this definition. Let me correct this. Actually, I want to say that this, so if you look at the set of vertices which are odd in this definition, that's called the boundary of the process. And if this set of vertices which are odd is empty, then we say that it's an even configuration. Okay, so I don't want any vertex to have odd degree, basically.
I'm completely confused. So you have a set of vertices and edges, and you have a 0, 1 process on that.
Yeah.
And now you want that there's no vertex in my graph, such that the degree plus the value of that vertex is odd.
Odd.
Okay, I think
exactly. Exactly.
Any reason why this is called the boundary?
There is a reason, but probably we won't get into that today.
Okay.
It's related to the correlation functions of Ising. But okay, so let me not get into that. So so this y and x, this differentiation between edges and vertices may seem a bit mysterious, but it's really, so another way to think of this graph is as follows. So if you introduce an external vertex, which people call the Ghost Vertex, and just add an edge from that Ghost Vertex to every vertex in your graph, and assign a weight y to those red edges, as I've drawn here, then the original. So then, if you look at the loop one model on this graph with no weight on the vertices and x weight on the base graph edges, and y weight on these red edges which I've drawn, then these are completely equivalent. Okay, so this percolation on the vertices is just another way to talk about the same thing, but on this enhanced graph. The reason we talk about it in this way, because we want to talk about automorphism, invariance, and things like that. And if a vertex has huge degree, then it becomes a bit messy to define those things. Okay, so of one important example is this the special case when y is actually 0 and x is 1. This is the model where it's a bond percolation model because y is 0, and x is 1, meaning that every configuration has the same weight. So it's a uniform even subgraph. So you take a finite graph and you look at the space of all even subgraphs and uniformly pick one of them. Okay, and this is going to be important in what's coming. So let's look at a few simple examples.
Wait. Sorry. So
yeah.
Even subgraph just means that the degree of each vertex is even, right?
Exactly. So y is 0. So in this case, you don't need the complicated definition.
Can you go up a little bit? So here you would have just to do a sanity check so that I understand. What is O of W? O of W is
the number of open edges.
So that's exactly the size of, so well, if x is 1, then it is just going to count 1, and so it's just going to be the uniform. Okay, I understand.
Yeah, exactly.
It need not even be connected.
No, it need not be connected.
Okay.
There's no, yeah. So it's a Bernoulli percolation condition to be even, if you want condition for every vertex to be even. Okay, so if the graph is a tree, so let's take a finite tree for the moment, and y is 0 again. So there is no cycle in this graph, and you can convince yourself that actually there is no even subgraph for a tree. It's the model is just the empty graph with probability 1, or all the vertices are isolated with probability 1. Okay, now let's look at the case when y is positive, and you're kind of still on a tree, but I took this segment example because it's just easier to draw, but it's essentially the same. So if y is positive, then there is some probability that you're connected to this Ghost Vertex description if you want, or the vertices are open. And in this case, you are going to get some collection of finite segments which are open with the open vertices on their endpoints. Okay, so this is how it's going to look. So now let's introduce some cycles in the graph, and cycles are important on even subgraph, as you might imagine. So if G is this cycle with x equals to 1 and y equals to 0 again, then you actually get the model is actually the whole cycle with probability half, or the empty graph with probability half, and there's nothing else possible. Okay, so so I hope these three examples gave you some idea of what even subgraphs or uniform even subgraphs will look like. And just for simplicity, let's just stick with x equals to 1, y equals to 0 for the majority of this talk. And essentially, it's going to boil down to that. So let me move on from now. So again, if you want to talk about factors of IID, you have to talk about infinite volume limits. So, and when you take infinite volume limits, if you're familiar with this area, there's two ways to take the limit. So you take an exhaustion of the graph, you take some sequence of increasing subgraphs which converge to G, or the union is G. And so there's two things you can do. One is you just take the sequence of graphs and take the loop one model on Gn, and hope that there is a limit as Gn as the union becomes G. And there's another thing you can do, which is also going to be of interest, is it's where you sort of clump every vertex outside Gn into a single vertex and erase all the self loops if you want, and just add, and this will create this graph. This is called the wired boundary condition, and hope that this has a limit as well. Okay. Now, one thing just to keep in mind, if G is the infinite three-regular tree, then you can see that there is a big difference between these two limits, if it exists. So in this case, the limit is always the empty graph because there's never a cycle in my exhaustion. But in this case, the limit, it's not going to be empty. I mean, you have to convince yourself of this. There's a little bit of argument, but it's not going to be the empty graph because there are all these cycles which will go through this wired vertex. Okay, so we'll come back to these later as well. Okay, so first of all, this existence of these limits needs some proof, but these limits do exist. Okay, and it was a question of Hutchcroft that whether these limits, whether they are factors of IID or not. And he had some motivation to understand these things from the context of spectral properties of measures. Okay, so just to put things in context, I've been talking about the Ising model a lot. So before stating the theorem, I wanted to emphasize where this weird model is coming from. So this model is actually something called a graphical expansion of an Ising model. Okay, so what is an Ising model? So I'm hoping everyone is familiar with this here, but let me still define it. It's a model on spins is what physicists call it. So it's either +1 or -1, and the probability of any configuration sigma is given is proportional to this quantity. Okay, so I should put a product here which was missing. So it's a product over e to the beta times sigma x sigma y. Okay, of interest for us will be something called the gradient of Ising. So it's a bond percolation model again, which you can get from Ising. How? Well, you take first an Ising model, and then for every edge you open it or put a 1 if the endpoints have the same spin or 0 otherwise. Okay, so that's the gradient of Ising. And how is the loop O1 model related to Ising? Well, it's actually related to the gradient of Ising. So the loop O1 model, the law of the loop O1 model, can be expressed using an explicit formula, which I didn't write here, in terms of the law of this gradient of Ising, which I talked about. Okay, so that's how they're kind of related to each other. There are other relations as well in terms of, if you want to talk about the correlation functions of Ising, you can also write it down in terms of the loop O1 measure. And so on, but in this work we only concentrate on the loop one measure and show how it can be expressed as a factor of IID. Okay.
One question. So this gradient is a function on edges, right? It is one only if the both. So it's somehow looking at the clusters as you were looking earlier. Like the first example, you were looking at clusters of ones and clusters of zeros. Well, there you were also flipping the sign, but here you don't flip the sign. You just look at that.
Exactly. So you're kind of losing the information. So if you look at exactly. Okay, so for Ising also there is an infinite volume limit, and now getting back to the question of whether things are factors of IID or not, because that's the focus here. So the plus Ising model, which is the limit which you can get by putting everything plus on the boundary of squares and letting the square go to infinity, this is always a factor of IID. So this is a result due to Ornstein, Weiss, Adams, and Hagström, Johansson, and Leon on various So Ornstein and Weiss did not publish the result, but later it was extended to all amenable graphs example, but it's or all graphs actually. So in any graph, the plus Ising measure is always a factor of IID. Okay, so this is of similar flavor to the example I gave, where of every infinite cluster gets a plus spin. It's not the same model, but it's of same flavor. Now, why can we prove this? How can we prove this thing is a factor of IID? Well, there's a tool which uses something called the Glauber dynamics, and another tool which is called the coupling from the past. I'm not going to get into these tools, but it's a fascinating idea. But the only thing I'm going to say is that there's something called monotonicity property of Ising, or sometimes they call it FKG, which basically says that if you increase the process on some vertices, then the whole process stochastically increases. That's really the idea. So this monotonicity of the Ising model is crucially used. And in fact, these ideas are so general that once you have some process which is monotone, you can apply some version of these ideas to understand whether a process is a factor of IID or not, or get a factor map. Okay, so this has been exploited a lot. So for the Ising model, the fact that it's a factor was proved in this thing by these people, and later there's this question of finitary factor, which was settled by Vanderberg and Steiff, and they actually showed in this remarkable paper that if the temperature is less than equal to the critical temperature, or beta is less than equal to beta C, or the temperature is bigger than equal to the critical temperature, then it's a finitary factor, and it's an if and only if. So in fact, in low temperature, the Ising model is not a finitary factor of IID, although it's a factor for the plus case. Okay, so if you look at monotone models, as I mentioned, but not necessarily Markov like the Ising model is, then there is also a result, and there is a whole bunch of results which about factors and relating it to spectral measures and spanning trees and perfect matching and things like that by all these people. I don't expect you to read all the names, but just to give you an idea of what has been going on, and if in case you're interested, you can Google and look up these papers. Okay. Now the thing I want to point out is that if you're not in one of these setups, and the setups includes whether you're in an amenable graph or not, which is mostly ZD, or whether you're a Markov model or not, like Ising, or whether you're a monotone model or not, like Ising.
I object vigorously. Amenable is not just ZD.
It's not ZD, but the tools go through. That's what I want to say. Okay, I mean tools for this specific question, whether things are factors of IID or not. In many cases. Okay, let me.
What does amenable mean? I am missing this terminology.
Okay, so a graph is amenable if you can get these exhaustions where the boundary is much smaller than the volume asymptotically. So in Z2, for example, the boundary of a square is of order n. If you have an n by n squared, but the volume is n squared. So but in a regular tree, the boundary is of same order as the volume. And it's historically the case that if you are in a non-amenable situation, these questions usually get harder. Okay, that's something I want to point out. Okay, but this...
there is one question I know, which I sort of know for ZD, but I have no idea in the amenable setting. Isomorphism, finitary isomorphism.
Yeah, of course, there are some things which are, of course, easier in ZD. So this sentence has to be taken with a grain of salt. Okay. So now so far I was talking about the plus Ising, but let's look at the free Ising, which is the Ising, which is the limit of the Ising model, but with no constraint on the boundary values. So if the temperature is high, then the free Ising on ZD, then the free Ising is in fact a finitary factor, but on low, if it's a low temperature situation, then it's not ergodic, so therefore it's not a factor of IID. But on non-amenable graphs, the situation is much harder. So here's the result. If So this tan hyperbolic beta equal to 1 over d minus 1 is the equation for the critical temperature on a deregulatory for Ising. So if the temperature is higher in this sense, with this threshold, then it's a finitary factor of IRD. That's basically the same proof as before, because every cluster is finite. But if it's higher than this threshold, then actually it's not a factor of IRD. This is a very strange result when you first hear about it, but it is the case, and it's due to the fact that the correlations somehow do not decay fast enough. That's somehow the idea here. So you can look up. So this was proved by Sly, and you can actually, Sly did not publish his result. It was proved in a paper by Leons. So this is a very, very intriguing result. And actually, if beta is in this range, then it's not known for the full range whether it's a factor of IID or not. Okay, so free Ising.
Vague memories of this. Is it also that it is not ergodic?
So
in the second case,
in this case,
yes.
So if beta is very large, I think, well, I mean, I think for very large beta you can probably say something, but I don't think up to this threshold it's not ergodic.
So you're saying, so I remember having a discussion with Matan at some point, and I remember that high beta definitely we saw that it was not ergodic. So you don't know whether up to the threshold.
Yeah, exactly. So yeah, of course it's not as trivial as that. So as the very high beta case.
So yeah, how does one actually prove that it's not a factor of IID?
Yeah, so I will direct you to a paper of Leon's. It's called it's called factor of IID on trees. Sorry.
Yes, to prove that it is a factor of IID, I mean, through your examples, it seems like there is a path. But to prove that it is not a factor, it seems like I have to rule out all the paths. But that's too much.
So just to give you some context, Shrikar, there are some, some things which your thing must satisfy if you want to be factor of IID is essentially isomorphic to IID, at least in the amenable setting. Non-amenable setting, I'm getting confused. I don't know. I think it's not true in the non-amenable setting. Anyhow, so to find something which has nice correlations, nice structure, and at the same time is not a factor of IID was open for a long time. So it's actually quite difficult in general to prove that something is not a factor of IID.
I see. So actually, so you also answered the second part of my question that I had not yet asked. That is, are there any equivalent statements for factor of IID? So you already mentioned that in the amenable case, you have the isomorphisms. No, morphisms.
Yeah, so there are several results several general results. So for example, if your process is a Markov random field, then with some monotonicity conditions, then you can say that this process is a factor of IID. If it's a Markov random field with certain fast decay of correlations, then you can prove that it's a factor of IID. So there are various results of this flavor, but
also connections with ergodic theory then, because if Markov random field with the fast decay of correlations, that would mean some sort of a mixing. So
yes, but but it's not really equivalent to mixing in most cases. I don't exactly remember if it's true for Markov random field, but there are examples of processes. You can look into the results by Ledraper. I hope I'm spelling it correctly.
Spelling is incorrect.
Correct. Okay. Sorry. So he had some constructions where this process was, I think k-fold mixing even. So if you have k different boxes, the processes decorrelate, but it's not a fact. It's not a factor of IID.
It has zero entropy.
And it has zero entropy. Yeah, exactly. So Yeah, so so there is all sorts of counterexamples, and this intuition that you have, that is fast decay mixing, it's the right intuition, but it's not enough in many cases. So it's a very nuanced thing.
Okay.
Okay, so let me mention a very recent result of Nam, Sly, and Zhang. It says that free easing in this it's related to this question. Actually, they prove that this is a factor of IID, but for large, this only works for large enough D, and there's also this constant here. Okay, so apart from, so if you're away from this sort of range, then this question is still open, and it's a very simple model. It's a Ising model on a tree. So even in this simple situation, you can see there are open questions. So it's a very nuanced thing. Okay, so let me just state our theorem. So just to give you another, before stating the theorem, just to give you another notion of the relation between this loop O1 and Ising. So on a planar graph, actually, so if you look at the gradient of the free Ising, so and you put an edge on the dual graph, and you open an edge on the dual graph, if and only if the spins are different, that is in the gradient of Ising, this edge is 0. Then you get some subgraph of the dual graph. You can convince yourself that that subgraph is actually an even subgraph, and in fact, that dual subgraph is a loop O1 model on the dual graph. Okay, and it's a wired loop O1 model on the dual graph. Okay, so there is a very geometric relation in case the graph is planar. Okay. Okay, so now back to the loop O1 model. The issue with this model is that this lacks monotonicity. Okay, so that's the big problem. So none of the previous techniques of this monotonicity and coupling from the past, which I mentioned, applies here. So you need to do something different. And so we have the two theorems here. But before stating the theorem, let me mention quickly that away from this monotonic setting, and there are many models which are not monotone, but it has some other properties, we really lack some general results. So if there is some nice properties which many models satisfy, which are not monotone, and developing tools to prove that those things are factors of IID are very interesting. So we do have these theorems, but it's a bit unsatisfactory in the sense that the methods are somewhat ad hoc, which only works for this particular model. But so yeah, so that's something I wanted to say at the beginning before stating the theorems. So here's the theorem. So in the wired case setting, we have almost full answer. So if xy is not 1 or 0, then it's a factor of IID. Now, if xy is 1 and 0, remember this means that it's really a uniform even subgraph. Y is 0 and x is 1. Then it's a factor of IID if and only if this graph G is not two-ended. Okay, it sounds fancy, but it's really not, because for example, if G is Z and you're looking at uniform even subgraph, then of course it's not ergodic, because it's either the full thing or nothing with probability half and half, because we're looking at the wired limit. Okay, so you have to be, there's something here, but not very nuanced. So the same idea sort of goes through in any graph which is not two-ended. Okay, I didn't define what two-ended is, but I guess you have some sort of geometric picture in mind of what an end of a graph is.
So I guess if I remove a finite connected component, then I'll have two subsets. I guess I can
exactly
get two components.
Exactly. That's one way to define it. Okay, now in the free case, it's the theorem is not very neat. So if y is positive, then actually we can prove it's a factor of IID. If G is amenable, then we know. There is a bit weird condition here, and this condition requires me to define the free FK Ising measure, which I really don't have time to define it, but it's a geometric condition, and it's a condition about geodesic cycles in the graph. So imagine you have, so this free FK Ising measure I didn't define, but imagine you have some subgraph of your graph, and the condition is that through every vertex, there are only finitely many geodesic cycles going through the vertex. Now, what is a geodesic cycle? Well, it's a cycle where the geodesic between any two vertices on the cycle is what you get by going through the cycle. So if you have a cycle here, you take any two x and y, the geodesic between x and y is this, this segment here. So this is a geodesic cycle, okay? So if you have only finitely many geodesic cycles going through a vertex of this weird subgraph, then we can say it's a factor of IID. As I said, the theorem is not very neat, but this is what we have. And if G is planar, then also we can say it's a factor of IID. Okay, so in the free case, it's not as complete as the wired case, but this is what we have, and the remaining cases are open. In particular, if G is non-amenable and is non-planar, that's the most interesting situation. Okay, so as a corollary, we get that the
one more question. So I guess so a tree would be a case like that, right?
Well, in a tree, the free. Well, unfortunately, in a tree, the free loop one is trivial. It's just the empty thing.
Right. You just said,
so you have to loop into a non-planar, non-amenable example. So
like anything that I can keep in
just,
mind?
I mean, there are some, you can look at 3D hyperbolic lattices if you want. Those are one standard things, but yeah. Okay, so actually I didn't mention in the definitions before, but all this actually extends even beyond the setting of vertex transitive graphs, and that's the setting of random rooted graphs. But I really don't have any time, so let me not get into that, and let me at least tell you how to go about this problem and without this monotonicity and how to understand this. So there is another model which is called the FK Ising model, and that model is actually monotone. Okay, so this is the definition of this model. It's a model on Born percolation. The definition of the model is not going to be very important, but the only thing I want to point out is that this model gives you another way to sample loop O1, which is in the following way. First, sample FK Ising. That seems good if you want to talk about factors of IID, because this is a monotone model. Then you sample a uniform even subgraph from your FK Ising model. Okay, so this is a Born percolation model, and you sample a uniform even subgraph from this. And if you do that, so it's really a uniform even subgraph. It's not the loop O1 model. It's the x equal to 1, y equals to 0 situation. And if you do that, then actually you get a loop O1 model with parameters x and y, where x is this and y is this. Sorry, x and y are related to p and this pH parameter here in this way. Okay, so essentially you have to understand how to sample a uniform even subgraph of graphs which are not really vertex transitive, but they fall in this category of unimodular random rooted graphs. So there is some symmetry in distribution for these graphs which are of interest. Okay, so we thought about this idea because FK Ising is known to be a factor of IID, again using this monotonicity. So actually, one strategy from here on would be to just sample FK Ising as a factor of IID, and then on the top of it, sample a uniform even subgraph of it as a factor of IID, and well, that will give you a loop O1 model, right? So you have to remember there's always these things about Y being positive, which is this magnetic field, and there's this notion of boundary conditions being wired and free. So a lot of technical things going on, which I am not talking about here, but these are all geometric. Okay. So the summary is to realize uniform even subgraphs as a factor of IID. Okay. So now how to do that? Well, let's again go back to the finite setting and try to understand how to generate a uniform even subgraph. So there's a very nice way to think about this, is to think about the even subgraphs as a vector space over Z2. Okay, so it's not very fancy. You just look at the set of all even subgraphs as a finite set, and you define addition in the following way, that you just take the symmetric difference between the edges. Okay, so for example, if you have some cycle like this and some cycle which schematically looks like this, you just remove things in the middle, and that will give you another cycle. And this is another even subgraph. So actually, if you add two even subgraphs in this way, where you just delete the common edges, then you get another even subgraph. And in fact, this defines a vector space over Z2.
So the even sub. Okay. So vector space. Do you mean vector space or group? It's just like I can add and subtract and all of that, right?
Yeah. So what I meant was Z2 to the
it's a Z2,
to the number of edges of
Sure. It's a Z2. Sure. Yeah. The Z2 vector space.
Yeah, yeah. Okay, but the only reason I want to talk about vector space is because I want to talk about the generating set or basis, if I want. And actually, here's the observation that if you take a certain collection of generating sets of your finite graph, and if you take some IID collection of Bernoulli half, and you add them, multiplying each cycle by 0 or 1, so you either take the cycle with probability half or not with probability half, then actually, if you take the sum, you get a uniform even subgraph. So this might have been more believable if I said take a basis and do this. But actually, since it's a uniform even subgraph and it's Bernoulli half, even if you take a bigger set, it's still fine. You can still add them or not add them with probability half independently and still get a uniform even subgraph. Okay.
So just to be concrete, if I take all cycles in the graph,
then also, yeah, exactly. You don't need to worry about whether you took the minimal one or not. Okay, that's a nice flexibility to have. Actually, here is a choice of this generating set. So we only care about generating sets now. So take a spanning tree of the graph. Okay, by spanning tree, I mean it's a tree where every vertex is included. So there's only one component, every vertex is included in that component, and it's a tree. And for the spanning tree, if you look at every edge not in the tree, then that gives you a unique cycle, because if you take an edge E, there is a path in the tree which joins the endpoints of E, and this gives you a cycle to talk about. And actually, if you look at the collection for every edge not in the tree, then that generates the set of even subgraphs of the graph. Okay, so this is the finite case. So then the question is, in the infinite setting, how to generalize this notion of the space of even subgraphs or generating sets, and then how to generate maybe this spanning tree in an invariant way, so as a factor of IID. Okay, so that's really the idea, and I really don't have any time. So let me quickly say that there is a very natural way to extend this notion of the space of even subgraphs on infinite graphs. You need to look at closures of spans and things like that. But once you define everything properly, then all you need to do is to select a generating set where every edge is included only finitely many times, because then you can add up this epsilon ICI, and this will almost surely give you a well-defined even subgraph. Okay, so this is what we call a locally finite generating set. So you want to get a locally finite generating set of your graph, and really it all boils down to, yeah.
If I was doing Z2, then I would just take cycle, like the minimal cycles, the 4 cycles.
Exactly. So Z2 is exactly in any planar graph, you can take all the finite cycles. You have to be a bit careful, because that generates for you the free space. The fact that it generates for you the wired space needs a bit more work.
Okay.
And it has to do with the space of ends and things like that. I really don't have time to get into that. But let me just push forward to the punchline. So the point is how to generate a tree as a factor of IID, which will give us this locally finite generating set. That's really, in the end, after understanding this even subgraphs a bit better, boils down to. And we choose something called a wired uniform spanning forest. So this is a very well-known object. And somehow this was, somehow we looked and I mean, there are various tools to understand this thing. This, if you know Wilson's cycle popping algorithm, this is one way to generate these guys. And it's a bit of work, but it's not too hard to prove that the wired uniform spanning forest is in fact a factor of IID. I didn't really define what these things are, but it's some tree, some forest, some spanning forest of the infinite graph. And once you have this sort of nice choice, you can get your locally finite generating set as a factor simply by choosing a Bernoulli variable for all these edges which are not in the forest. Okay. However, this wired uniform spanning forest gives you the generating set for the wired space. It doesn't give you the generating set for the free space. So, and what gives you the generating set for the free space? It's the free uniform spanning forest. But unfortunately, the free uniform spanning forest is a much less understood object, and we don't know how to generate that as a factor of IID. Okay. Anyhow, so I think I am almost over time. So, I probably won't have.
Shrikar and Kaushik and Atul need to leave. Are you in a hurry? Then, so Atul doesn't say so, and Shrikar and Kaushik, I don't know.
Okay, but yeah. So let me maybe stop here and go to the last page. And so one thing maybe I can point out here, given the amount of thing I was able to say. Yeah, so in the non-amenable situation where where the graph is infinitely ended, and think not a tree, okay? So think of something else, okay? Some other graph which has infinitely many ends. So it kind of looks like this. Okay, so, and it's like a tree, but okay. So what's a good general choice of a locally finite generating set? So that's really a question of interest. Okay. So locally finite generating set, which generates which generates the space spanned by all the finite cycles. Okay. And not the wired space. Yeah, okay, I didn't really define any of these things, so maybe these questions which I wanted to talk about doesn't make any sense, but let me maybe finish with this question. So
but
if you go back
sorry to interrupt.
Go ahead.
Just because you drew this picture, and also that we talked about non-amenable, non-planar graphs.
Yeah.
Have people looked into Cayley graphs with a specific generator? Because then, I mean, because you have a lot of control through the generating set.
Exactly. Even for Cayley graphs, if you have some good construction of a locally finite generating set for the free space, that would be very interesting. So here's the picture. So if you have a non-amenable graph, then the wired uniform spanning forest looks like this. Every component of the wired uniform spanning forest has one end for every end of the graph. So that's how it captures every sort of cycles which are wired but not free. So this is the picture. So that's why we could generate the wired space. However, if you want to generate the free space, which is the one generated by only finite cycles, then somehow you have to eliminate all those cycles which go through infinity. Which are not generated by finite cycles, because finite cycles can only generate by infinite paths. So here's maybe. So finite cycles can only generate by infinite paths which are in the same end. Okay, this by infinite path might be generated by finite cycles. So imagine sort of having something like this.
Yeah, I understand.
Yeah, but if you have a by infinite path going through different ends, then it's not going to be generated by in the free space. So somehow, if you can give a way to generate the free space, in this sense, you have to eliminate all the by infinite paths which don't go through different ends as a factor of IID. There are ways to generate it if you remove the condition that it's a factor of IID. Okay, so you just do some brute force, select a sequence of vertices, look at all the cycles and so on. There's a construction in the paper by Griment and Janssen, but it's very much non-invariant. So it starts with ordering the set of vertices and selecting the vertices in order. So that kills everything about being invariant. Okay, so you have to generate it in a nice way, like here.
So about this question of yours, give me one particular example which I can think about. So I was first thinking about non-amenable. I was thinking about SL3Z or something of that sort, but that's not a very good choice because I guess it's not infinitely ended. Do you have
so the usual you can look at, for example, okay, so so you have to also look at a non-planar example,
right?
Yeah, so I'm not really a group theory person, but I'm a probability person. So I'll talk about the example I'll give is a supercritical percolation on one of these hyperbolic lattices. So if you take a supercritical percolation, it will have infinitely many ends. But I'm sure there are Cayley graphs also which looks like this, which are not trees, which are not planar. I guess if you look at something like a tree cross tree, maybe.
But it will still have finite. What am I talking about? Of course, yeah, that will have.
Yeah, maybe that's a good example. Yeah, but the example I always think about is this percolation cluster. Yeah, exactly. Okay, so let me maybe also mention this thing. So this coupling which I talked about with this FK Ising, that only works if x is between 0 and 1 and y is between 0 and 1. So even understanding the loop O1 model beyond these two settings, like having even the existence of infinite clusters is I think open. So if you take x, you could take x bigger than 1, then we don't know. And one reason is that the connection with Ising falls apart if x is bigger than 1. Okay, so how to understand that is also open. Okay, maybe let me stop here.
So let's thank Gaurav for this wonderful talk.
Thanks.
Very nice talk, Gaurav.
Thank you. Yeah, very nice talk.
And sorry for being I don't know, irritating.
Oh, no, thanks.
So,
no worries.
I would have irritated more, but then at some point I thought that maybe I'm doing.
Well, I didn't have to talk about the proof more since you asked me.
But yeah, questions. I think.
I don't know if it's good.
But yeah, go ahead.
I want to ask. So I'm not at all an expert in this thing, but so you mentioned that this factor of IID is kind of like it implies ergodic and mixing properties, but so does it imply something extra than these kind of? So we already know. Suppose we already know ergodic and mixing property, and we also know. So what kind of extra property does follow from?
These properties are not really equivalent. So there are all these examples where things are Bernoulli, but not really, not mixing or K mixing or things like that. So these properties are not really equivalent. I guess one property which is of interest for ergodic theorists is this notion of entropy. And in fact, on ZD at least, and probably in the more general setting of amenable graphs, if two processes, if x is a factor of IID of y, if x is a factor of y, not just IID, I guess, then the entropy have to be equal. And in fact, it's an if and only if thing. So, but unfortunately, the non-amenable setting, as far as I understand, this notion of entropy is not very well developed. I mean, there's probably some paper by Bowen on this, but how to describe entropy is
Lewis Bowen.
Probably Nishant.
There's more Bowens. There are too many Bowens in this world.
Lewis Bowen, yeah. So yeah, probably Nishant can tell you more about this, these directions than me.
But I can add one thing that just to what Gaurav said. See, one is of course this idea of mixing. That you understand that if you go far enough away, then you are independent. But under suitable assumptions on the space, maybe you want to say more. For instance, that the tail is 0 or 1. For example, do you have a Kolmogorov 0-1 law for your random process? And under more assumptions and the fact that it is a factor of IID, this would be implied. But these are all weaker than being a factor of IID. It's in certain settings, it would be a very strong decay of correlation. You can say some very strong statements once you know that it's a factor of IID.
Yeah, another motivation is from the algorithmic perspective. So this factors of IID tells you that there is a local algorithm which allows you to simulate these processes. But I guess these things starts becoming more interesting once you have some quantitative bound on how large this sort of this radius you need to look to in this IID process to simulate this. There are various applications of I mean, if you can prove something is a factor of IID, there are various applications. So there's this pretty nice series of papers due to Virag and some other co-authors like Harangi and Bachhaus and other people, where they prove various properties of certain processes called Gaussian wave processes. So if something is a factor of IID, then they can prove something about the spectral properties of these processes. So there are some applications in that direction as well. From my perspective, I just find these questions interesting in their own right. Just take a statistical physics model and can you, and as you can see, it's a nuanced question because take a simple example of easing on a tree, the free easing on a tree, which is really a Markov chain. Essentially, it's a tree index Markov chain, but whether it's a factor of IID or not, it's a very nuanced question.
And one more question. So you mentioned that when you have like Markov property, then these kind of questions is well understood, is it?
On amenable setting.
Okay. So
exactly. So I mean Markov plus some more things. So I guess if you just a Markov random field on ZD, I'm not sure if there are some
complicated things. Yeah, it can be whatever you want.
Yeah, it can be very complicated, but sort of getting an if and only if theorem.
Does that mean that it applies to Gaussian free field kind of stuff?
Okay, so if you're talking about the discrete Gaussian free field,
yes,
then I think it will follow from one of the papers of Virag, where he talks about these Gaussian wave functions. So you can look at that. But of course, there are other variants of Gaussian free field, like where so this is more difficult because here the space in which the spins, the values which the spins take is non-compact. So for example, if you look at these models like the SOS model, or this integer valued GFF or things like that, I guess these are all open. I mean none of these things are known. So as I said, these methods are somehow I guess Virag's methods are more general than ours, but these are somewhat ad hoc, adapted to different
I see.
different models. So if there's some general idea, oops, if there's some general idea like which works for non-monotone models, then it's going to be very interesting, at least for me.
Okay, thank you.
Yeah.
Thank you.
Other questions? Let's thank Gaurav again.
Thanks for having me.
He sent his apologies saying that he had to leave, but
That's okay.
all right, I should stop recording.